So I wanted to quickly make a video about Hamming codes to explain the generator matrix and specifically the P part or the parity part of the generator matrix. So just here we have the message being sent. This is the generator matrix, the transmitted word or the Hamming code. Here I have an error which I can use to apply an error to the received word. So if I put, say, a 1 in here, that changes that to a 1, or a 0 in here, it'll change it to a 0. Pretty simple. And this is the parity check matrix. Obviously, this is just an identity, and this here is the transposed version of this matrix up here. You can see in here, each of these just refer to a cell up there. So this refers to I6 up there. So any message that comes through, because I haven't applied any error, our syndrome down here, which is the description of an error, is all 0. So I can change that to a 1 as well. So our syndrome stays as 0s. But if I now apply an error here, our syndrome changes. So immediately a receiving device would know that there is an error. So what you do with a syndrome is you look across your parity check and find where the parity check matches the syndrome. So we can see here that matches the syndrome. So we would know that the error is in this bit in the received word. And by doing that, the receiver can correct that error. And that's basically how it works. Now, something a lot of people ask about is how do you generate this matrix, the P? That can basically be anything, but because of the way this parity check works, or the way the syndrome used the syndrome to scan across the parity check, you want every column in here to be unique. Because if we used, say, if I change this here, if we used this as our P matrix, then this column here is the same as this column. And now if I put an error in, we get the correct syndrome, but we don't actually know which one it is. So it's important that in your parity check, across your entire parity check, every single column is unique. And that informs how you develop the P matrix up here. So a lot of people will find it easier to develop the parity check matrix first. So all you do is you write the identity, and then you come up with several columns that are unique. So there's no other rhyme or reason other than they need to be unique. Now, as you get larger, you can do some fancy things where if you have, I'll just fix this here. You can do some fancy things where if you have 2 errors, you can work out there's essentially a binary addition going on here with a binary addition with a modulo. But this right now just appears to be an error here. So you wouldn't actually be able to detect this error correctly. Well, you would correct this bit and you would have an error, which means you would need a larger error or a higher level error checking to detect that. But when you do get larger matrices, you can do some interesting stuff with developing this parity check matrix. So your Hamming distance increases and you can essentially find multiple errors with a single syndrome. But on this size you can't. But anyway, that's basically it. That's how these work. I'll just quickly click through these so you can see this is just the sum product of these columns, modulo 2. That's for all of these. And this is, like I said, it just has an override. So if that's blank, it will use the transmitted word. Otherwise, it overrides with the error. And that's basically it. That's how this works. The syndrome is the same. So these are all just matrix multiplications. I've just laid it out like this, so it's easier to understand. And that's it.